So I have to admit, this whole course is not actually my stuff. But I do like super fancy bioinformatics data structures. But I still like most of the, so I'm recording there, I'm recording here. I really find most of the stuff in this course, and I have to start this, most of the stuff in this course is like really fascinating to me. This last bit after the NP completeness, I teach this because the other professors insist that you have to know this. You have to, like Norbert says he wants people to know, I forget if it, I think it's Floyd Warshall or Bellman Ford or something like that. And it's like, really, why isn't Dijkstra good enough? So you'll see today that there are instances in which Dijkstra's can't deal with it. But then, so there are cases like on sparse graphs, there are faster algorithms, but I don't think we're going to get to that today. On DAGs, there are faster algorithms. We're probably not going to get to that today, but those are fairly easy algorithms. The one on DAGs is anyway. So Bellman-Ford is also fairly easy. So you'll remember from the last lecture, so Dijkstra's algorithm, so you're the corrupt county planner who's going to arrange everything for their own convenience, and so you're going to pave the roads such that you can get from wherever you want to wherever you want as quickly as possible. And it doesn't matter if this costs the taxpayer extra money, and it doesn't matter if it's inconvenient for everyone else. They will still be able to get everywhere by paved roads because they can just travel from where they live to where you live and then follow the path you would take. So they would follow the path you would take from your place to their place in reverse, assuming it's a non-directed graph. And then they would follow the path you would take. So yeah, it's connected, but it's not minimum cost overall, and it's not minimizing the distance for everyone else. And also, Dijkstra's algorithm, from the proof of correctness, we remember it cannot deal with negative weight edges because we had this bit where you say, oh, okay, so you have like the greedy proof. You say, oh, well, if I marked a distance wrong, then it was one step away from the stuff I've marked correctly, assuming up to step I, our solution can be extended to an optimal solution, blah, blah. So we haven't made a mistake up to step I. On step I minus 1, we label the distance of the closest vertex that can be reached in one step. Right? So where the distance to the vertex you would jump from, and then the edge cost is minimized. And then you can say, okay, but so then if you were to get to it another way, you would have to leave this stuff we've already correctly labeled, but that means that you would have to go from there to somebody who's one step away. And then that, by the way we're processing the vertices, is large. I shouldn't be waiting. This has nothing to do with Dijkstra's algorithm. This has negative edge weights. And then you would have to say, okay, but then you've already gone further, or at least as far as our distance to this new vertex. But then what if you have a negative weight edge? Then you could say, okay, but then I can, this distance is now 10, but in this distance, when I jump out by one step, is 12. But then I have an edge weight with weight negative 9. So great. So today we see all pairs, shortest path. Well, first we see how to deal with negative weight edges. Okay, we can't deal with negative weight cycles. At least you can sort of deal with a negative weight cycle in a graph if it's not reachable from your starting point. Oh no, it is recording. Okay, it's not reachable from your starting point, but we don't care, because that's actually not going to show up in this algorithm, because if it's not reachable from your starting point, then you're not actually going to find it. Okay, so what is Bellman-Ford? It's actually sort of, it's more general than Dijkstra in that it can deal with negative weight edges, but it's sort of a slower and like if you're really pessimistic and you didn't trust anything, you might run this. So what is it? Well, we'll see. So you start out and you say, oh, I forgot to label these. Do I have to label? This is STU whatever. Yeah, I think, does it really matter? I think this was Z, U, V, W, X, whatever. So, okay, suppose we're starting at Z. So we say, maybe this red is readable now. Okay, so the distance from Z to Z is 0. Okay, fine. That's good so far. Now, what we're going to do, and initially we label all of these with distance infinity, which means this is an upper bound, right? It's not maybe the real distance. There's no way to get from Z to some vertex, then this distance is actually infinity. But this is just our upper bound, our estimate, which is possibly too high. Now, the idea behind this algorithm is, okay, if there is a shortest path, if there is no negative weight cycle, okay, if there is a negative weight cycle that you can reach, then it's best to just keep going around it, right? Because that means that the vertices on the other side, if you keep going around the negative weight cycle and then you come out and you go to those vertices, then you could have done that more cheaply if you'd gone around the cycle once more. Okay? So assuming there are no negative weight edges, because that messes everything up, the shortest path now from Z to somewhere is going to consist of a finite number of vertices. Like you're going to start at Z and you're going to go somewhere and you're going to go somewhere and actually it's going to be at most n vertices. So the thing is, these vertices are not going to repeat. You're not going to have a loop, right? Because you wouldn't. Why would you put a loop in? It can have a weight at most 0, in which case you can ignore it. It can't have a negative weight by assumption. So there's always going to be a shortest path in which every vertex that you visit is visited once. It's not a Hamiltonian path, you don't visit every vertex once in this path, but any vertex you visit, it's visited at most once. Okay, so what we're going to do is sort of consider all of those paths, but in a slightly efficient way. It's sort of a bit like dynamic programming. So this means, so we're going to assume that every shortest path, where shortest doesn't mean the number of vertices, it means the total cost of the edges. Every shortest path is going to have length at most, is going to have, okay, so it's going to have length at most n minus 1. Okay, because the length of, like if you have a vertex and an edge and another vertex is considered, it has 2 vertices, but it's length 1. Okay, so that means, so we're going to run the algorithm at most n rounds. Okay, so at the end of the ith round, we want to maintain the invariant that everybody whose shortest path is at most I steps from Z is correctly labeled. And then by the end of it, you can say, okay, so everything at most n steps is correctly labeled, so we're done, because everything is within n steps. So let's do this. Oh, right, and so we're going to do n rounds, and in each round, for every vertex and every edge leaving that vertex, you have some vertex U, and you have V1 and V2 and V3. Okay, And these are labeled with some distance, okay, possibly infinity. And if u is labeled with infinity, then, well, you can still do it, but it's kind of pointless. So what you're going to do is see, okay, so this edge we're going to see, say it has cost 1, cost 2, cost 3. And what you do is for every vertex, you consider its outgoing, all of its outgoing edges, and you say, okay, so distance to V1, so d V1 equals min of d V1, and then d, oh, and so this is the distance at the current moment. So this is what we're updating to, and this is the distance at the current moment. So it's like variables in C. It's not like this is the I is equal to I plus 1. It doesn't make sense. In this case, it does. So du plus C1. Oh, that's not closing parenthesis. And then you want dv2. No, actually, that's dv1. No, that is, I didn't want to stop right there. Sorry. Like I said, I'm a bit zoned. Okay, and v2 is dv2 equals min dv2 du plus c2. Yes. Okay, d3, no, v2. dv3 du plus so for every vertex, so it may be that this is distance 5, and this is distance 2, and this is distance 6. In that case, we don't change it. Right? We only change it if this is distance 5, and this is distance 2, and this is distance 8, then we say, oops, no, we found a cheaper way to get here than with cost 8. We found it with cost 7, so we say, nope, not 8 anymore, it's 7. So, so there are n rounds, okay, one for each, one for the maximum possible, one for each vertex and the maximum possible length chain. And then for each, so the n rounds, for each round, we consider all the vertices and consider all of the edges leaving it. Okay, and then, so that seems to be n square. Just a sec. I don't remember the running times of these things over there. So, yeah, it seems to be, doesn't seem to be that slow. Yeah, okay. Oh, it says, this is complicated. Yes, okay. Time, so this is Bellman-Ford. Okay, yeah, it is only about as fast as I thought. It's, so for if we have n rounds, for each round we're going to, at each vertex, we sweep all of the outgoing vertices, so that's m. So it's going to be m times n, so it's all of m times n. Okay, and the neat thing is, if you don't have a negative weight edge cycle, but you have a negative weight edge, this will find it. Okay, if it finds, oh right, and I have to tell you how at the end you detect if there's a negative weight edge, a negative weight cycle. So if there's a negative weight edge cycle, so after you do all of this, so you run this recursion for each vertex, and you run it as many times as sort of the depth of the, okay, really tired. So how do you find out if there's a negative weight cycle? So what you do, so this works because you can see that eventually, so by induction, before you take any steps, Z is labeled correctly. After you take one step, everything whose shortest path is one step from Z is going to be correctly labeled, because you've looked at Z and the shortest path, it's any other way to get here is going to be at least as long as the shortest path in one step, the path in one step, because we're assuming that these are the vertices we're considering, the ones whose shortest paths are one step long. And so it's going to get replaced with the correct distance. And then after 2 steps, the things whose shortest paths from Z are of length at most 2 are labeled correctly, and so on. So after n steps, you're done. But what if it has a negative weight edge cycle? So then you think, okay, if there's a negative weight cycle, I need this sleep point. Okay, so you think if this has some, you have some distance labeling here, and then you think, okay, so if this is cos C1, this is cos W plus C1, this is cos C2, this is W plus C2. And you go around and you think, okay, if this actually added up to a negative number, so if the total weight of the cycle is a negative number, then you can't have the right label everywhere. Right? So if you have the right label, then always this is going to be some, okay, this is going to be some W prime, and then this is going to be some C prime, and then this is going to be less than or equal to W prime plus C prime. Okay? But if you have a negative weight cycle, then when you go around, you can, if you go around often enough at least, well, but if you go around once, you've got to have the case that this end is going to be too big, right? Because assume that so if I start here, that if I go here, this is at most this weight plus this cost, okay? And this is at most this weight plus this cost, and this is at most this weight plus this cost, and so on until I get back to here. But then, if you take, it's like this weight is at most this plus this cost. This weight is at most this plus this cost. So that means that this is at most this plus this cost and this cost. Right? So you go around and you get back here, and it's like, okay, well then this weight is at most this plus all of these costs. If those costs are negative, you're getting that this weight has to be smaller than itself. So that means that if you have a negative weight cycle, then somewhere there's an edge where you've got U has weight 1, and this has weight C, and here you have V, and it has weight 2. But you're going to have W2 is greater than W1 plus C. So somewhere there's an edge where this doesn't, normally you have, if everything is worked out, you have the constraint that W1 plus C is bigger than or equal to W2. But if you've got a negative weight cycle, then you can find an instance of this. So after you've done the n rounds, you just check all of the edges. Okay, any questions about that? Like I said, I'm not super on the ball today. Anybody still there? I have 11 students out of like 99 in the course. Okay, any questions about Bellman-Ford? That was easy, right? Maybe T will bug me up. Okay. Okay, so the next bit I do get a bit interested in because, okay, so like I said, if you have a graph that's a DAG, then you can topologically sort it, and you can find single source shortest distance faster. But we're not going to get into that. Did I start this? No. Maybe. Yes. Okay. So the next bit is this matrix multiplication stuff. So multiplication is in quotes because it's not exactly multiplication. It looks a lot like multiplication, but okay. Yes, I still have this graph. Goody goody. Oh, and this, so Bellman-Ford is a single source algorithm. You pick, in this case, you pick Z and you move around and you find how to get to everything with the minimum cost from Z. The all pairs shortest path algorithms are computing simultaneously the shortest path between any two vertices in the graph. And this, I think, also works for negative weight edges, but nothing works for negative weight edges. Like in negative weight cycles, I'm really tired. So how would this work? So this is a bit like, we're going to see this sort of this idea again in a minute in Floyd-Warshall. But the shortest path from A to B is either from A to B, okay, assuming no negative weight cycles, is either A to B, or A, and then some path to somewhere, and then some path to B, right? So we can consider, like, okay, if we know sort of the distance to all the possible intermediates, then we can sort of take two of these distances and glue them together and get the next round. Okay, I'll show you. So let's suppose we've decided that we're going to go from A to somewhere and then to B. And we want to figure out what's the shortest way to go from A to somewhere to B. Okay, so you would write a for loop, right? I wish we were in class. First of all, I wouldn't do this. I don't stay up late working when I have to actually be somewhere. And the bike ride would wake me up because it looks nice out. And I would be able to see you and ask you questions. So I would be making you do this, so I could sit down and drink tea. So you're trying to get from A to B. So the first thing you consider is go directly from A to B. And then to get from A to C and from C to B. So how would you, if you somehow knew the ways that you could do this in one step, right? You would say, oh, well, okay, this is going to be easy. For C in vertex class minus A minus B. I don't know if you actually have to, okay.